My name is Caleb Huntington, and I'm a fourth-year PhD candidate in the lab of Simon Anthony at the University of California, Davis. Before beginning my PhD, I served as a public health associate at the Centers for Disease Control and Prevention during the COVID-19 pandemic, contributing to the national response. That experience shaped how I think about pandemics, not just how we respond to them, but how we might prevent them in the first place. Now in my PhD, my research focuses on understanding how pandemics emerge in the first place. A lot of research efforts concentrate on what happens after a virus spills over into humans, developing vaccines, testing antiviral drugs, and evaluating public health interventions. While these are critical components of pandemic preparedness, they are also reactive. A more proactive approach begins earlier, in the pre-emergence phase, by understanding how and when viruses move from wildlife into people. This is where wildlife viral surveillance comes in. By monitoring viruses circulating in animal populations, we can identify potential threats as well as the factors that increase the risk of viral spillover. Wildlife surveillance presents a major challenge. The world is vast, ecosystems are complex, and we often don't know where or when to look. Deciding which geographic regions, seasons, or host species to prioritize can feel like searching for a needle in a haystack. To address this challenge, I took inspiration from a powerful tool used during the COVID-19 pandemic: wastewater surveillance. Wastewater sampling is a form of environmental monitoring that provides a snapshot of viruses circulating at the community level. It does not rely on testing individuals one by one, and instead it captures population-level trends efficiently and non-invasively. Now, unfortunately, wildlife populations do not have convenient sewer systems for us to tap into. So I began exploring whether environmental air sampling could serve as a parallel approach. Although air sampling has been used in agricultural and indoor environments, its use in natural wildlife systems has been extremely limited. To test this idea, I've been working with bat populations in Puerto Rico. In this system, we collect environmental air samples from a bat cave while simultaneously collecting biological samples directly from the bats. This paired approach allows us to capture what is detected in the environment with what is actively circulating in the animals. What we first found is that we're able to detect many different types of viruses through air sampling, including coronaviruses, which we certainly care about from a spillover perspective. When we look at our results from 2 months of intensive air sampling, we see patterns of viral shedding start to emerge. Not only do we detect the viruses, but we also capture shedding dynamics that can be used to guide targeted individual sampling and inform the risk of spillover happening in a system. Ultimately, this work aims to shift pandemic prevention from reactive to proactive. By developing scalable, non-invasive tools to monitor wildlife viruses, we can better understand when and where spillover risk is highest. With that knowledge, we can make smarter decisions about surveillance, preparedness, and intervention. I'd like to thank ARCS for their support, without which this research would not be possible. So thank you.